In today's class, we will discuss about conductivity, drift and diffusion current. So what is meant by conductivity? So for the conductivity, we got the relation in the last class, the intrinsic conductivity sigma I is equal to NQ mu N plus PQ mu P. So this is intrinsic semiconductor conductivity. That means the conduction is going to be occur due to both electrons as well as holes. So the electrons conductivity is going to be represented with NQ mu N, as well as the hole conductivity is going to be represented with PQ mu P, where N is number of electrons, P is number of holes, and Q is charge of the electrons, and mu n is the mobility of the electron, mu p is the mobility of holes. So this is the entire intrinsic semiconductor conductivity. Similarly, if we are going to take extrinsic semiconductor, in extrinsic semiconductor we are going to have either the majority carriers or either electrons or holes. So the conductivity is, if the conductivity is occurs due to n-type semiconductor, in n-type semiconductor the majority carriers are holes, so the conductivity is going to be equal to only n into q into mu n, or it can be represented as nd into q mu n, where n is the number of electrons and nd is the donor ion concentration, both are same. And if you take p-type semiconductor, sigma p, the conductivity due to holes is going to be equal to pq mu p. Why? Because the majority carriers are holes in p-type semiconductor, and or we will take it as an acceptor ion concentration. Sigma p is equal to Na q mu p, or we will take this expression nq mu n pq mu p. So in n-type semiconductor, the conductivity is, major conductivity is due to only electrons, and major conductivity is due to holes only in p-type semiconductor. But in intrinsic semiconductor, the conductivity is due to both electrons as well as holes. So in intrinsic semiconductor only we can consider the conductivity is due to both electrons as well as holes, but in extrinsic semiconductor, if it is an n-type, the conductivity is due to only electrons. If it is an p-type, the conductivity is due to only holes. So in the intrinsic semiconductor, sigma I is going to be equal to nq mu n plus pq mu p, as both electrons concentration and holes concentration is same in a intrinsic semiconductor. We can write it as n equal to n equal to pu equal to Ni. So I can write it as Ni, and the charge also is going to be same, Ni into q mu n plus mu p. So sigma I is going to be equal to Ni q mu n plus mu p. This is for intrinsic semiconductor. But for extrinsic semiconductor, it is due to both it is due to only electrons, or either it may be due to electrons or holes. So sigma n is equal to nq mu n. So this is in n-type semiconductor. If it is in p-type, pq mu p. This is for p-type semiconductor. So in semiconductor, the current is due to both electrons as well as holes. So in n-type semiconductor, the current is due to electrons in n-type semiconductor. In p-type semiconductor, the current is due to majorly holes. So what is mean by drift and diffusion current? So before going to know about what is mean by drift current, we have to know about what is mean by diffusion current. So the diffusion current is going to occur due to concentration gradient. So what is mean by concentration gradient? So if a material is having some majority carriers, suppose if I am going to have a p-type semiconductor, in p-type semiconductor the majority carriers are holes, these holes will try to move towards the n side. So I am having a p-type semiconductor. Similarly, I am going to have an n-type semiconductors. Almost the majority carriers are holes in p-type semiconductors. So as the n-type semiconductor is having less number of holes, the holes will try to move towards the n side. So at the junction x is equal to 0, more number of holes will try to move towards the n side. So as the distance x is going to be x increases towards the n side, the number of holes is going to be decreases. So at the junction x is equal to 0, the number of holes from p side to n side is more at x is equal to 0, but as the distance x is increasing, the number of holes is going to be decreases. Why? Because it is having, as the length increases, the number of holes coming from p side to n side is going to be decreases. So it is the constantly exponentially decreasing is going to be happen. So the current which is forms due to the this process is called as concentration gradient, where the more number of holes coming from p side is going to move towards the n side. So this process is called as concentration gradient. So the current going to be formed due to this type is called as diffusion current. Similarly, there are more number of electrons present in n side. The majority carriers are electrons. Similarly, there are minority carriers, holes also present in n-type semiconductor. Similarly, the electrons also present in p-type semiconductor as minority carriers. Here also the holes are present as minority carriers in the n side. As the majority carriers are more or electrons, these electrons has more concentration in n side, they try to move towards the p side. So at junction x is equal to 0, more number of electrons will try to move towards the p side. So at distance x is equal to 0, more number of electrons is diffused from n side to p side, but as the distance x is increasing, so the number of diffusion length of the electrons in p side is going to be decreases, and it is also exponentially decreasing nature. So this process is called as diffusion current due to holes, and here the current occur is due to diffusion current due to holes present in this process here, and here the electrons are moving from n to p. This is the diffusion current due to electrons. So the diffusion current I suffix p due to holes is going to be written as minus q into dp by dx. Similarly, the diffusion current, so the diffusion current due to holes is I suffix p is equal to minus q d suffix p dp by dx. Similarly, the diffusion due to electrons is I suffix n is equal to plus q dn into dn by dx. So why we have mentioned here minus q dp by dx for diffusion current due to holes, and here plus sign for diffusion current due to electrons. So let's see here, if the more number of holes has been moved from p side to n side, so as the number of holes is going to be decreasing in nature from x is equal to 0 to particular distance up to the length of the n-type semiconductor, as the holes are decreasing, always we know that the current is always in the direction of holes movement, or it is in the opposite direction of electrons movement. So as the holes are decreasing in nature, concentration gradient is going on decreasing, so the current also is going to be decreases. That means the current forms also decreases from x is equal to 0 to some up to the length of the n-type semiconductor. Therefore, as it is in decreasing nature, we have kept minus sign here. So similarly, if you take here, as the electrons movement from x is equal to 0 to some particular length L, the electrons is going on decreasing in p-type semiconductor, which has been come from n-type semiconductor. As the electrons are decreasing in nature, but the current direction is opposite to the movement of electrons, current will be forms like this. So as it is exponentially decreasing the electrons movement, the current diffusion current due to electrons is going to be formed in opposite direction. So it is in increasing in nature. Therefore we have kept plus sign for diffusion current due to electrons. So this is the difference why we have kept minus sign for diffusion current due to holes, as well as plus sign for diffusion current due to electrons. So we know that what is mean by diffusion current. Similarly, we are having what is called as drift current. So diffusion current is going to occur without applying any external electric field or potential to the semiconductor. So to the semiconductor I am not going to apply any electric field or potential. Then this diffusion current is going to be occur due to both holes as well as electrons. But if I am going to apply an electric field to a PN junction diode like this, if I am going to apply a potential to the PN junction diode, so what will happen, the holes from P side will move towards the N side. Similarly, the electrons coming from N side move towards to P side. So this movement will forms the current. That current is called as drift current. So the drift current will occurs only when an electric field is applied to the PN diode or semiconductor. But when the diffusion current is going to occur when there is no electric field applied, and this current is occur due to concentration gradient, but the drift current is going to occur due to applied electric field or potential. So the drift current due to electrons is going to be equal to N into Q into mu n into E, that is applied electric field or potential, V or E. This E is going to be calculated by velocity by distance, that we know that. So N Q mu n into E. So where N is the number of carriers, that means number of electrons due to number of electrons, Q is the charge of the electron, mu n is the mobility of the electrons, E is the applied electric field. Similarly, the drift current due to holes is going to be occur is equal to PQ mu n into E, where P is the number of holes, Q is the charge of the hole, Q is mobility, mu P is the mobility of holes, and E is the applied electric field. So totally we are having diffusion current due to holes as well as drift current due to holes, diffusion current due to electrons as well as drift current due to electrons. So totally the current forms due to holes is diffusion current plus drift current. If it is only holes, what is the current? Diffusion current due to holes plus drift current due to holes. If it is the current due to electrons, diffusion current due to electrons plus drift current due to electrons. So we can see the formula here. The total current density is equal to drift current plus diffusion current. So the total current density due to electrons is going to be equal to Jn is equal to drift current Nq mu E plus diffusion current Q dn by dx, where dn is the diffusion constant of electrons and dn by dx is the how many number of electrons has been changed with respect to distance x. Similarly, J suffix P diffusion total current density due to holes is equal to drift current due to holes and drift current due to holes as well as diffusion current due to holes. So this is the total concept of drift and diffusion current. And we are having an important two note points, note 1 and note 2. So what is this important points is, if I am having an external semiconductor, that means an external semiconductor wants to excite, that means from valence band to conduction band. If an electron has to move from valence band to conduction band, and it is with having an energy gap of some 1.1 or 1.2 electron volts like that. So how much amount of wavelength required to make that valence electron to become as free electron is going to be calculated as going to be calculated by using the formula E suffix G equal to 12,400 electron volts by lambda in the units of angstroms. So 12,400 by lambda. If it is in the terms of micrometers, 1.24 by lambda micrometers if the wavelength is lambda. So if if an intrinsic excitation is going to be occur, and the relation between energy gap and wavelength is going to be E suffix g equal to 12,400 by lambda in the terms of electron volts, or in the terms of micrometers the wavelength has been given, then it is equal to 1.24 by lambda of micrometers. And we know the basic formula. The relation between resistivity and conductivity is equal to rho equal to 1 by sigma, and the formula for resistance is equal to R equal to rho L by A. So where rho is equal to resistivity, L equal to length, A equal to cross sectional area, and already we know that sigma is equal to conductivity, that is equal to NQ mu N. So these are the important formulas what we have to know before solving the problems in GATE examination previous year questions. So it is a GATE 2003 question. So the question is, an n-type silicon bar of having 0.1 centimeters long and 100 micrometer square cross sectional area, so has a majority carrier concentration of 5 into 10 power 20 per meter cube, and the carrier mobility is 0.13 meter square per volt second at 300 Kelvin. If the charge of the electron is 1.6 into 10 power minus 19 coulomb, then the resistance of the bar is. So what is the data is given? So you want to calculate the resistance of the particular semiconductor material what we have taken, and he has mentioned it is an n-type silicon material having an 0.1 centimeters long. So that means he has given the length 0.1 centimeters, and cross sectional area A is equal to 100 micrometer square, and the majority carrier density of 5 into 10 power 20. So as he has given it is an n-type silicon, so the data he has given is Nd or n suffix n is equal to 5 into 10 power 20 per meter cube. So the data he has given is length, area, and the donor ion concentration. N suffix d is equal to n suffix n equal to 5 into 10 power 20. So how come we know this one is, it is an n-type silicon bar, 5 into 10 power 20, and the carrier mobility, so mu n, carrier mobility is 0.13 meter square per volt second. So the temperature he has given as 300 Kelvin, and the charge also is given 1.6 into 10 power minus 19 coulomb. So these are the data what they have given. So what we have to calculate is resistance of the bar. So from the formula, resistance R equal to rho L divided by A. So this is the formula what we have seen before, resistivity into length divided by cross sectional area, and already we know that the resistivity is going to be inversely proportional to conductivity, so we can write it as L by sigma A. So we know what is the formula for conductivity. For n-type semiconductor, the conductivity is going to be NQ mu n into A. So where n is equal to n suffix n, that is equal to Nd. So L is equal to 0.1 centimeters they have given. So if it is converted into meters, we will get it as 10 power minus 3 meters. So 0.1 centimeters can be converted into, in the terms of meters, as 10 power minus 3 meters. And similarly 1.6, the charge of the electron is 1.6 into 10 power minus 19 coulombs, and n is going to be, the value of n is going to be equal to 5 into 10 power 20. So 5 into 10 power 20 if you take, and the mobility value is given as 0.13. So 0.13 value also if we are going to substitute, and what is the remaining thing is cross sectional area. Cross sectional area is 100 micrometer square. So this 100 micrometer square is written as 10 power minus 4. Why? Because micro in the sense 10 power minus 6 into 10 square, 10 power minus 4 you will get. So if we are going to solve this, we are going to get the resistance as 10 power minus 1 ohms. So this is the answer, R equal to 10 power minus 1 ohms. So the option is C. So the next question is, the electron concentration in a sample of uniformly doped n-type silicon at 300 Kelvin varies linearly from 10 power 17 per centimeter cube at x equal to 0 to 6 into 10 power 16 per centimeter cube at x equal to 2 micrometers. So the data he has given is the electron concentration is varying in a semiconductor at 300 Kelvin varies linearly from 10 power 17. So it has been started at 10 power 17 at x equal to 0 and to 6 into 10 power 16 for a distance of 2 micrometers. So up to x equal to 2 micrometers it has been varied as 6 into 10 power 16. So the electrons variation is going to be decreases from x equal to 0 to x equal to 2 micrometers.